What's up, what's up? Welcome back. Today we're working on my x86 operating system, StreamOS. It's an operating system that we've been developing on Stream. And we're starting to see some form of like a thing come together, right? We've got like a thing it boots, it has like memory allocation, it has like concurrency, serial output, logging, like an Ethernet stack, which means that we have like HTTP over TCP, which involves like ARP, which is like address resolution, Ethernet, etc. PCI, because you need like a PCI card to talk to. Like the Ethernet card that we're using virtually is a PCI card. We've got some sort of graphics and keyboard and multi-core, which we just wrapped up recently. And what we're working on today is USB. So if I just like maybe do a quick little demo here, is our operating system. It's booting in QEMU. We've booted it with like 8 cores, and it like is distributing work to those 8 cores. So here we have like a little bit of like some graphics proof showing that we have like keyboard input. I can play this little brick breaker game. And if I like go to the IP address of this guy, he's like serving an HTTP thing that we can see from the browser, and we go like, hello. And it says like, hey, we got a form with we saw the word hello. And if I like spam refresh on this guy a few times, in our logs, which are forwarded to our standard output by our virtual machine, because we're like logging to the serial console, and that gets like forwarded to standard output, we can see like we're being serviced on like different CPUs as we go. Great, everything's working. What we're working on today is USB. So in the past couple streams, we started looking at USB 2.0 and USB 1.0. Let's see, we can look at USB on the OSDev wiki, and we can maybe look at like EHCI. Oh, that's gonna put a little bit of a pause on this. But anyways, we're looking at like UHCI and EHCI. And the idea is that like USB started, they had these cards, they implemented this like standard specification. There were 2 standard specifications, OHCI and UHCI. And those are like how like the specification for how you interact with cards. I think I read that Intel pushed one and the other one was pushed by someone else, and so they both stayed around. Then they get to like USB 2.0 and they go, hey, we need to go faster. We need a new standard because we have like things that we need to cover that weren't in the previous one. And so we were looking at like the first stream we did on USB, we were looking at detecting like an EHCI card. And then we kind of were like, oh, that's like looking kind of complicated. Let's kind of back up to finding a UHCI card, which is the USB 1.0 version. And what we want to do is we want to like be able to like detect our mouse using UHCI. And we got kind of stuck. We like found the card. Let's see if we can like look at where we got to last stream. Are we in the right spot? Yep. Let's go back. Just go back to the default. Here we go. And what did we do? We enumerated PCI cards. We found the one we wanted, and then we started looking at like, oh, we've like found some of these registers that are in the UHCI card, and we can talk to them and like see like somewhat expected values. Like here we see a status register for the port change depending on if we have a thing in there or not. So we have like some sort of proof that we're talking to the card. And then the next question was like, well, now what? Like, how do we actually do USB stuff? And I read this pretty good book. I think it's called USB, the Universal Serial Bus. I took yesterday off to try to like, off the streaming to try to figure it out. Maybe I call it book. This guy, he wrote this book, USB, the Universal Serial Bus, and this book is sick. It like basically like I just started reading like it front to back on like the parts that I cared about, skipping chapters that weren't important, and that really cleared a bunch of stuff up for me. So if you're looking for like a like tutorial, this guy's got you covered. But basically, what we were missing is like, how do we like actually talk to USB? So we like look at this like USB stuff on the OSDev wiki, and they're like, well, like what's the first thing that we'd want to do is maybe like talk to a device, right? Like we want to see like what's plugged in, and here they talk about setup. Yeah, here they talk about like issuing setup transactions. You're like, what the fuck is that? Like, how do I do that? Because you look at this like UHCI page, and it's like, oh, there are like registers here, but like, what do I do? And the answer is, when you look at your like UHCI card, this is like a physical piece of hardware plugged into your PCI, and he's in charge of like talking to the USB devices. You like even the ones like on the back of your motherboard, those are still going through like the PCI bus, just without like the external connectors, whatever. And let's see, what is he doing? So you set him up to say, here is like a list of shit to do. Well, like. And what the UHCI card promises to do is he's like, I will like execute each of these things in my list once per unit of time, which is like a confusing concept, right? So you're like, if I wanted to like, say I'm like here, and I'm like 1 millisecond later, I want you to send this packet. You would like put this packet in here. And that's like kind of confusing because then now you're like racing the card essentially. You're like, well, where are you and where am I inserting stuff? And that's a little like scary, like hard to deal with. And so you might ask like, why the fuck do they do it this way? Where they get to the end, he like goes back to the beginning. He's like, why are we doing it like this? And the thing that the book said they're doing, which I think makes a lot of sense, is they're basically saying, if I instead of putting a unit of work in here, let's say this is like a pointer to a unit of work. Like work 1. And you could actually point every single thing in here to work 1, and it will execute that once per unit of time. And so then you start to think, oh, I see. So what you can actually do is work 1 can actually point to another unit of work 2, and he can point to another unit of work 3. And so what you can do is you can have these like things that you want to execute at like certain rates, and you just get those for free, because what you can do is you can have like each of these guys, you can have like this guy point to work 1, this guy point to work 2, this guy point to work 1, this guy point to work 2. And what ends up happening if you do that is every tick you'll execute work 1, and every 2 ticks you'll execute every tick you'll execute work 2, right? Because you're either executing it as like a subtask of work 1, or you're executing it directly. And every other frame you'll execute work 1. And so you can actually start getting things like your mouse might say, hey, please poll me every 16 milliseconds. And instead of you having to like interrupt your CPU to set that work up every 16 milliseconds and like queue it at the exact right time, you can just put it in this like 16 millisecond gapped queue, and then you will like automatically execute it through the card, which is pretty sick. And so when they talk about things like, hey, you're going to issue like a setup transaction, what that means is you're going to like put that in one of these queues of work to do, and then the card will like do the USB packetization stuff to make that happen. Another piece of info that I didn't really understand until I read the book the other day was everything you do in USB is like host controlled. So a device can never say, hey, the mouse moved. Listen to me, I moved the mouse. Instead, what has to happen is you ask the mouse, hey, how often are you going to update me? And he says like, once a millisecond, I guess. And I go, okay, so every millisecond, I'll ask you where you are. And so that's how this works. This is a little oversimplified. For UHCI, I think this is a UHCI specific thing. I'm not actually sure. I think it's a card side thing, not like a USB protocol thing. There is a unit of work called like a transaction descriptor, and you could put transaction descriptors in here. But that doesn't let you do this thing that we were just talking about, where you can like set up like timed work. And so what you actually usually do, or what the book is suggesting that you do, I guess, is you would instead start a queue. And a queue is just like a list of transaction descriptors. And so what you can do is you can have like TD1, TD2, TD3, and these guys will actually link together. So each descriptor will say, oh, the next thing I want to do is this guy. And so what happens is like this queue has this mechanism saying like, well, when you point to here, I'll execute this guy. and every time I execute, I'll like update to his next thing. So this will happen like the first time, the second time, and the third time. And so what you can do is you can just like append to these queues, and they'll like do these units, these like chunks of work, I guess. And then you have these things where you can like actually have queues point to queues as well. So like you could, instead of having this be a transaction descriptor, you could have this be like this queue will point to Q2, who points to Q3, who points to transaction descriptors. And then it gets like additionally complicated because you can also have queues point this way, as like they call them horizontal and vertical. So you can have like Q4 here, and he's like a whole separate section of work. And that's how you split up like the different polling rates, basically. So like what you could do is you could have your like Q1 be your 1 millisecond polled queue, and then Q3 be your like 16 millisecond polled queue, and then each of these guys will have like queues that represent like transactions that you want to do, and each of these guys points to transaction descriptors. So what I want to do today is like start building up these data structures. Right? The idea is like once we initialize the card, all we have to do is like set up our queues, stick them in here, and then we're like ready to go, essentially. Then all we have to do, if we can like easily construct transaction descriptors and queues, then we can like automatically, we're like ready to do like actual USB interaction. The other thing to look at is this UHCI standard. Who's this guy here? And there is a better diagram than the one I drew that basically shows the same thing. This guy. How do I zoom in? Right, so this is essentially drawing the same thing that I just drew out, but better. So you have this like frame list that is where you tell the card to read from, this like circular buffer essentially. And he can point to either transaction descriptors or queues. And the queues point to transaction descriptors. Great. Transfer descriptors. I've been using the wrong word this whole time. Yeah, so I think we can just start jumping into it. So let's do that. Okay. So what do we want to do? We want to I guess generate this structure. So let's just start stubbing it out and see what happens. So I think we have a UHCI module, great. And in here we can just start making up stuff. So we can say like struct transaction descriptor. Is that what they're called? I'm second guessing myself now. Transfer descriptor. God damn it. Transfer descriptor. And let's just start like looking at what this guy has like conceptually, and then we'll think about like data layout after maybe. Or is that how I want to do this? We could also just yeah, that is how I want to do this. I was gonna say that we could just start like stubbing out. We could do this like make a packed struct, but I don't think that Rust has any like good like bit field stuff going on. So I think probably what we'll do is we'll make this like a user, like a in-memory representation of this thing, and then we'll make like a serialization function that turns it into like the packed format that you see here. Or what we could do is we could just store him directly as this. How many bytes is this? This is 1, 2, 3, 4 32-bit words. So we could just store that. We could make this a 4-byte U32 array. And then we could make setters and getters for each of the fields. So we could say like link pointer, and he takes himself, and he returns a, I guess a pointer to a new transfer descriptor. Is that what it is? Let's see. Link pointer corresponds to a memory address. This field points to another TD or QH. So I guess we'll just say we'll make him return a U32 pointer for now. But I think that there's a good chance that we'll want this to be like, maybe this should be like an enum. Yeah, because we can tell whether or not it's a transfer descriptor or a Q head. But we'll get to that later. And how do we pull this guy out? So this is the first word. So this is the first word. And we're just gonna, I guess we take, if I remember correctly, the reason that this is packed this way is this is a 32-bit pointer, but the bottom, the 32-bit pointer knows that it's pointing to a 32-bit thing. And so that means that it has to be 32-bit aligned, which means you can pack extra shit into the bottom 4 bits. And so that's what they've done here. So the pointer itself is just the first byte and masked off the top n bits. So this is a, we cast this to U32. Great. Great. So there's a couple extra pieces on here. So one of these is telling us whether or not it's a valid thing. So if terminate is set, this is the link pointer is not valid. So this should actually return an option or maybe an enum. So we'll say enum link pointer. And the options are, it could be either nothing or a transfer descriptor with a, let's call it TD for short. And we'll say that this is a pointer to a transfer descriptor. Or it could be a Q head, which is a pointer to a Q head. And for now, we'll just make our Q head nothing. So we'll say struct Q head. We'll figure this out later. And now what? So now our link pointer will return a link pointer. And we will, first we'll say, let word, I guess, D word, double word, I think is what they call it. Well, D word is the double word, which is 32 bits essentially, is self 0, 0. We'll say that the, we'll match the bottom 2 bits, I guess. So we say if D word get bit 0, if the terminate flag is set, we return link pointer none, right? There's no valid link. Then we say if D word get bit 1, the Q head pointer thing, this select, he says, if it's 1, then it's a Q head. If it's 0, then it's a transfer descriptor. So here, I guess we say the pointer is this guy. And if it's set, then it's a return pointer as const Q head. And then we say link pointer QH. Else, this is a transfer descriptor. Wonderful. And he doesn't like that they've got returns here, so wonderful. And this guy doesn't need brackets around him anymore. Great. Cool. This seems like the kind of thing that we should be unit testing. So we'll start pulling in our unit test infrastructure. So it's use, create, testing, everything. We create a test. And this is because we do it this way because our unit tests can't use the normal Rust test infrastructure where you would just write like a test, function test, and like assert false. This doesn't work for us. Mainly because what this would end up doing is it creates like a binary that it uses a built-in main function that will iterate all of the tests that it finds that are constructed with this macro. And that doesn't work for us because we don't have like a normal main. Our kernel is like booted by the virtual machine, and he like does some like assembly bootstrapping, which jumps us to our very specific function. And so what we have instead, we're using this like Rust unit testing thing that lets us register a test as a like test case. This is like a nightly feature that we can use. And then we have like a way to retrieve all the test cases and iterate them and run them in our own kernel context, whatever. So we've all kind of wrapped that in a macro where we say like create test, and we'll call this test td link pointer. And then we make our function. And for us, instead of asserting, you return a result. So if we do this, I think if I run cargo test, we should see a failure, or we should see this test exist and pass. So somewhere in here, we should see our file, UHCI, test.td link pointer, okay. And if I write like error failed to run test, this should fail. Right here, failed to run test. And what's kind of nice about this is like we then get an exit code 1 that we've like flagged to the virtual machine. We say, hey, please exit abnormally. And we do this by like QEMU. We like pass in a device that we can write to that kills the VM with a specific exit code. Pretty cool stuff. And so now what we can just do is we can just start like punching in, we can like make one of these by hand and see if we get the right thing out. So if we said that our thing was, let's see, let mute dword equals 0, we'll say, I was going to say that we can just like construct one manually here, but I don't really like that. Specifically because we're actually going to want to be able to like write these guys as well. So maybe I'll write like a set link pointer as well. And we'll call this link pointer. And let's see, what do we do here? We do the opposite, right? We say our thing is going to be 0. And if it is none, so we'll say match pointer. And if the pointer is none, what are we going to do? We don't really care about anything except for the terminate bit. So here we're going to say dword set bit 0 to true. And we're going to use our little like helper class for getting and setting bits. Now I know that this is like a less efficient version of doing all of the masking and shifting ourselves, but it does give us the benefit of being able to just think about it more naturally. So here we'll set this at bit 0, and then we're probably done. If we have link pointer td, we set this to 1. So set bit 1. And sorry, do we set it to true or false? False. Right, we're looking at this. 0 equals td, 1 equals qhead. And so if we have, I guess this is, we don't care about the content yet. And then here, if we are a qhead, we set bit 1 to true. And then here we have pointer comes in. I guess we'll call it val, pointer val, I guess. Here we say dword or equals pointer val. as U32. So the reason we're doing this is because we know that the pointer val's lowest 4 bits should probably be 0, and so we can actually probably add an assertion for that too. We'll say assert that the pointer val get bits from position 0. We want 4 of them. We just want to assert that that's 0. So we'll say assert equal, and we'll do that for both. Get bits is wrong, because this needs to be as U32. Wonderful. And maybe we put a comment on here that says pointers are guaranteed to be for 32-bit aligned. There we go. There we go. Now, I guess you could argue that this shouldn't be an assertion. Maybe this should be like a returned, like we could return a failure here. But if I'm constructing these with invalid pointers and I crash my kernel, I'm fine with that, especially in the context of us making like a little toy operating system. Okay. So now all we have to do is set the D word. So we'll say I guess here, first of all, this needs to be mutable. And maybe we should preserve the bits that we didn't try to set, like these guys. So maybe this should actually be, this is equal to self.0, 0. And now we have to be a little careful. This or equals is no longer valid because we don't have the guarantee that the initial thing was 0. So here probably we should set, how we do this. We say D word set bits from bit 4, and we have the size of an int -4, so that's 32 minus 4 is 28. And the value is pointer val shifted right by 4. It doesn't like that for some reason, because this needs to be as U32. There we go. So now the rest of it should be preserved. And then I think all we need to do is say self.0, 0 is equal to D word. And now we can do a little test that just tests that like the set and get is right. And that doesn't really check validity entirely. But it does help. It does like kind of how to say this? If it at least proves that our two versions match each other. So I'll derive debug, EQ, and partial EQ for this guy so that in our unit test we can like compare equality of the link pointer. And then we'll just say let word is equal to link pointer td x dead beef, but dead beef is not a line, so we just say dead b as a transfer descriptor. Is that what it's called? I already forgot. Transfer descriptor. And we will construct one of these guys. I guess we need to say we need like a new function here to make one of these guys. And I guess we take in a U32 for. Maybe there's no point in making this new function if we're gonna do this. We can just make it by hand. So let's just do that. We'll say let td is equal to mutable. Mutable td is equal to transfer descriptor, which is just 0 4 times. And then we can say td set link pointer to val. I guess we could manually compute what we think this should be. So we should say TD 0. We can say test that this is equal to, and what do we expect to see here? We expect to see 0 dead B, and then what do we expect to see here? We expect to see terminate false. We expect to see Q head false. So we should see 0 0 here. Okay. And then we can also test that we get back the same thing. So we can say TD link pointer to val. Wonderful. Wonderful, wonderful, wonderful. Let's see if that passes. We're already getting problems, so they don't like that this is a move here, so we can just pass this in by reference. I think I write ref here. No, I dereference this. And this. Okay. Cargo test. Do I compile now? Still a problem. Literal out of range for I-32. That's weird. I guess I'd just write U32 here. Weird. Okay, so that passes, which is good. That's very good for us. And now we can just do the same thing, but with a Q head. I guess we can say test TD link pointer TD. And then copy paste this for a Q head and none. Okay. So for the Q head, this will now be a Q head, and this has to be a Q head. Great. We do the same thing here where we construct our transfer descriptor. Here we set the link pointer, and now we expect a different number out. Instead of 0, 0, we expect 0, 1, because, or 0, 2, I should say, because bit 2 gets set, sorry, bit 1 gets set, which makes it 1, 0, because it's interminated, which should make it, that's the number 2 here. Great. And the rest is the same. And here we do the same thing, but this guy says none. And so we expect this guy to just be the value 1. Because this should all be 0, this should all be 0, and only the terminate bit should be set. Let's see. So if we run cargo test, do we see any failures? Nope, looking good. Okay. Okay, so that's this part done. So here we'll just make like a subsection, I guess, and we'll say we're at 3315, and I guess that means that here at 1235 we were working on link pointer, and now we're on 3330, and we're working on word 2, I guess. So what's in word 2? All this shit. Host controller read write, host controller read only. So this is the stuff that the after we ship it into the controller might update these fields. Okay. So what do they call this? Control and status. Okay, so we'll say control and status. So what is he in here? SPD. Function. So short packet detect. When a packet has this bit set to 1, the packet is an input packet in a queue, blah, blah, blah. I wonder if we can just like assume for now that this will be 0. Like we don't have to, how do I say this? I think that we can write all of this to 0 initially. Let's see what's in here. Short packet detect. When a packet has this bit set, the packet is an input packet, is in a queue, and successfully, then the TD is marked as inactive. Okay. This bit is a 2-bit down counter that keeps track of the number of errors detected while executing this TD. So we can set it to be 0 for no error limit. Low speed device, I think we probably will want to toggle this. And we'll want to toggle this as well. ISO synchronous select. So we'll probably want to set this to 0 normally, but we might want to set it later. Interrupt on complete says that like when you finish this transaction, please trigger an interrupt. There's a status flag, which I don't know if we should set initially. What does it say? This field is used by the host controller to communicate individual command execution states back to the host. This field contains the status of the last transaction performed on this TD. For isochronous TDs, this is always the completion status. For other transfer types, this field is updated each time the TD is executed. The bit encodings of this stuff. So this is error received, detected, error stalled. Hold on. Doorbell's ringing. Be right back. Sorry about that. Yeah, so this can all be 0 initialized, I think. Actual length field is written by the host controller at conclusion of USB transaction to indicate the number of actual bytes that were transferred. It can be used by the software to maintain data integrity. The value programmed in this register is encoded as n-1, maximum length field, and TD. So it looks like some of these I'll want to set, but a sane default value for all of these guys is probably 0. So maybe I'll just ignore that for now. Maybe that stuff might not be that important yet. We'll see. It's possible that for like the setup stuff, I won't need it. Very possible. Okay, so this is the TD token word 2. So that's this stuff. And this is stuff that like control stuff that we almost certainly want to put in, right? Like device address, max len, PID, that all sounds important. So let's implement that. Okay. So the fourth word, oh, oops, that's not what I want. I want third word, TD token. So one of these things is max len. And what is his maximum bits? He's got 21 to 31. But is okay, so he says bits, it's +1, I think. The maximum length field specifies the maximum number of data bytes allowed for the transfer. The maximum length value does not include protocol bytes such as PID and CRC. Okay. Where PID is packet identifier and CRC is probably like error checking. The maximum data packet is 1280 bytes. The packet length is longest. The 1280 packet length is the longest packet, theoretically guaranteed to fit in a frame. Actual packet maximum lengths are set by HCD according to the type and speed of the transfer. Note that the maximum length allowed by the USB specification is 1023 bytes. Okay, I see. Note the values from these are illegal. Okay, so we basically say you could give me an input value of 0 to 1280. So we'll say length is a U16. And we say assert that len is less than 1280, less than or equal to 1280. Here we're seeing that len should minus equal 1. So we'll make this mutable. And we'll say if len is equal to 0, len is equal to 0x7ff. That's what it says there in the spec sheet here. It says if it's 0, then we should use 7ff. Otherwise, len minus equals 1. Now, this is just fucking weird. I don't understand why they do it this way. But I'm sure that there's probably some like hardware optimization reason. But it is weird. And then we just say that's these guys, bits 31 to 21. So len set bits. We shift by 21. The length is 10. Unless it's 11. Is this an inclusive range? If we have 0 to 3, 4 to 31. Yeah, it's inclusive range. So this is actually 11 bits because it includes bit 31. Right? Am I crazy? 31, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Yeah, that's 11. That is 11. Okay. So I think that's it. Oh, and I need to pass in len, of course. Oops, this is wrong. This isn't len set bits. This should be self 0 word 2. Like this. Like this. Okay. And then we can also get the maximum length. Which is just the inverse of this. And so this should be this should just be get bits. Like this. I think that's it. Okay. So here we can test TD max len. And we can just do the same thing here. So we say the value that we want to set is, we'll try the two ends. So we'll say 1280. We want to try 0. And we also want to try something, probably want to try 1. And we want to try something like normal. So we'll say let test vals equal to this. So I guess I append a comma, join, delete the equals. There we go. Those are reasonable test values. We'll say for val and test vals, we want to check that if we set the max len to val, I guess we probably also want to check the like in-memory representation here. So we'll actually do this. We'll say here are what I expect you to write as the once we put you in. So this should be 299. And we'll say this is val expected. We'll say what? We'll say memory in mem. And okay, then we can say set the max len to this. Test equal that the value is equal to what we get back. We say td get max len. And we want to test that the thing at word 2 get bits 21, 11 bits. We want to test that this is equal to the in-memory expected value. Okay, and we can power test and see if that fails. Ooh, it sure does. It says here at 169. 1280 does not equal 1279. Right, because of course, we just, on this like get bits, we just didn't convert it back, which is like fucking stupid. So we'll say let ret is equal to this. Ret plus equals 1. And if ret is equal to 0 to 7 of f, we return 0. Else we do this. Okay. Test again. And there we go, we're good. So our edge cases are passing and the normal case passing, great. Wonderful. Let's just do a quick checkpoint here. Checkpoint, because I'm worried that I'm gonna fuck something up beyond repair. Data toggle. This bit is used to synchronize data transfers between a USB endpoint and the host. This bit determines which data PID is sent or expected. The data toggle bit provides a 1-bit sequence number to check whether or not the previous packet was completed. This must always be 0 for isochronous TDs. So I think I read about this, and the idea is that if I like send like 4 things back to back, I alternate their numbers just to make sure that we didn't fuck something up. I guess I don't really fully understand why that exists, but I just know that we do have to toggle it back and forth. So we'll just say set data toggle. And we'll take in value as a Boolean. And we'll get the data toggle. And so this is just bit 19. So we say self.0 word 2 set bit 19 to val. And here we just say self.0 word 2 get bit 19. And he returns a bool. Wonderful. Wonderful, wonderful, wonderful. Another unit test. So we say test td data toggle. And this is easier. We just say set data toggle to true. And then we say make sure that the data toggle is true. And we do it again for false, I guess, just for peace of mind. And normally, like in the other ones, we're actually testing the memory representation. But I think that if we did this, we would just rewrite the data toggle functions. There's no point. No point. All right. All right, all right. Endpoint. This 4-bit field extends the addressing internal to a particular device by providing 16 endpoints. Right, so for each USB device, he has multiple interfaces and endpoints. So I don't really remember, I don't know if interfaces are addressable, they must be in some way. But this is basically saying, which of the endpoints are we trying to talk to? Like, you can imagine that one device might provide multiple capabilities, and you might want to, like, separate those out logically. Like, if you had a integrated keyboard and mouse, you might want your keyboard and mouse to have different endpoints or something. So this is just bits 15 to 18. Which is these guys. Great. So let's just smack that in there. So set endpoint and get endpoint, I guess. What did I just do? What the fuck? What the fuck? Okay. So here let's replace data toggle with endpoint. This value is going to be a 4-bit field, so this is a U8. We assert that the value is less than 16 because it's only 4 bits. And then we say self.0, like the value that we're trying to set, word to set bits, and we are setting bits 15 through 18, which is 4 bits, and we're setting that to val is equal to 2. And here we just get bits. Yeah, there we go. As you wait, I guess I have to write. Okay. Write a little test for that guy. So we say test td endpoint. Okay. And in here we just say set endpoint to 0x what, like FD or something. Endpoint, and we just test that it is 0x FD. I don't think there's much more testing to do here. It's a pretty straight pass through. Oops, this is just not less than 16. That's 255. Because why is this a 4-bit field, like 16? Why is this 4 bits if it only has 16 endpoints? Oh, 4 bits, not 4... Yeah, what am I talking about? This is 8 bits. I'm just an idiot. Oops. Oopsies, oopsies, oopsies. There we go. So that's passing. Great. Great, 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 great. What's next? Packet ID. So here, same thing. We delete the internals, replace, oopsies. Endpoint with PID. My packet ID can be 8 bits, right? 0 to 7. And so we say self.0 to get bits, 8 bits here. And here we just say set bits, and we replace val as equal to. And this is the same. We do endpoint and replace endpoint with PID. There's actually not really much else to do here. Not much else. It's the same shit. Now, probably at the very end of all of this, I'm going to make one test that's like test manually constructed TD, and I'm just gonna make one by hand. And that makes sure that like if there's anything that I've like actually made a mistake on in terms of like bit manipulation, that we'll catch that later. So let's just double check that that exists. Great. And then I'm actually going to comment this out for now because I just don't want to deal with... I want to like see the test passing if the test that I'm working on is finished. Okay. So now the buffer pointer is the data buffer pointer for this transaction. It points to the beginning of the buffer that will be used during the transaction. This buffer must be at least as long as the value in max length field described, and the buffer may be byte aligned. So this is just a pointer to data. So I guess this is just a pointer to mute U8, probably. Yeah. Yep. And this will return a mute U8. Probably. Maybe this should return a const U8. Not really sure. We'll figure it out later. Or maybe we won't figure it out later. Maybe we'll just never think about this again. And this guy will just be... like this. Right? Because this is the third word, right? 0, 1, 2, 3. Great. Great. There we go. Easy. Easy. And we do another PID data. And here we say dead beef. And we expect this to be dead beef. Wonderful. Oh, shockingly doesn't work because I forgot to cast this. Like this. Wonderful. Wonderful, wonderful, wonderful. All right. So I think this is done. Other than the status stuff, but we're far from there. And then there's also D words 4 to 7. So there's actually an extra 4 bytes at the end of this. Not 4 bytes, 4 words at the end of this. That we can use to like track stuff internally. So this should actually be where do I find this? I wonder if it has to be that long. It does say they're reserved. So probably we do have to allocate something that's that long. 16 byte boundaries. There are 4 different transfer bytes. 16 byte boundaries. Okay. TDs are formatted identically. The default different transfer types are supported by a small number of control bits in the descriptor. All transfer have the same basic 32 byte structure. Am I high? 4, 8, 12, 16. Oh, yeah, okay. So 32 bytes is divided by 4 is 8. So this should be 8. And just anywhere where I wrote 4 here, I'll replace with 8. And I just will double check all of these as I'm replacing. Looks good. Looks good. So yeah, I think I read that you can like punch in like pointers to like things that you want. I don't know. I don't like some tracking stuff you might want to put in there. Not sure. I don't really have any ideas for what that would be, but I will keep in mind that they exist. Okay, so I would say that like probably the transaction descriptors are like pretty ready to go. I think that we could like make one now. And so probably the next thing to do is the queue head. Let me just double check that there isn't anything else in here. TD token. Yeah, nothing else in here really that we're missing. Next up is the queue head. So we'll say like at 58 minutes, like implement queue head. Let's just do a quick checkpoint so that I don't break anything. And maybe we'll like do a quick, like even maybe say something in here, like checkpoint, TD is ready to go, kind of. Okay, so what the fuck is a queue head? Queue heads are special structures used to support the requirements of control, bulk, and interrupt transfers. Since these TDs are not automatically retried after each use, by their maintenance requirements can be reduced by putting them into a queue. Queue heads must be aligned on a 16-byte boundary. So I wonder, do I have to like write align? Rust align struct. Can I like just write align me on 16? Rust set alignment of type. I can just put repr align. Nice. Nice, nice, nice. So here I should probably say repr align 16. Wonderful. Wonderful, wonderful, wonderful. Okay. So now we have to like work on this queue head shit. It is time. And let's just maybe update the timestamp here. 01. Oh. Okay. So queue heads are pretty straightforward, it looks like. They are D word 0, D word 1. Oh, that's it. Just 2 words. Easy. Easy. So this is U32, 2. And what are we doing here? We have the Q head pointer and the link pointer. So we'll say impl Q head. And these should also be aligned on 16-byte boundaries. Wait, does it say 16-byte or 16-bit? 16-byte. Okay. Okie dokie. Let's see. So here, we're just going to say set head link. Takes myself by mute. And we have like a val. Which I think can just be a link pointer. And I think this actually looks the same as this guy. So we'll factor this guy out. We'll say set link pointer. And I guess we'll take in a U32 to write to. So we'll take an immutable U32, as well as the, so call that destination. And we'll say the val is a link pointer. This. And we'll probably have to write like a get link pointer too, from some source. And he returns a link pointer like this. Wonderful. So this guy just gets this. This guy gets this. We have a little bit of fixing up to do. Like this. And here we have to change some of these guys. Wonderful. Wonderful, wonderful, wonderful. Okay. Yeah, that looks good. So now here we change this link pointer to say get link pointer of self, the first word. And here we do the same for set link pointer. But he takes in this by mutable reference and sets pointer. Then the rest of this goes away. Wonderful, wonderful, wonderful. And if I cargo test, nothing should fail. We should still have our like get link pointer setters and getters looking good, which they are. And all of this like UHCI tests are still passing. And now I just do this like I can do this where I have the head link as well as the element link. And these guys are implemented the same way the TD ones were, where the getters use get link pointer, the head is number 0, and the element is number 1. And these are the same. So this is number 1, and this is number 0. Okay. Wonderful, wonderful, wonderful. So I think the Q head's actually pretty much done. I guess we should probably write a quick little test. These functions should not be outside the test module or after the test module. And we can just say what? Create test QH. We'll say QHead. Because later when I read the test and I see they're failing, I'll be like, what the fuck is a QH? And here we can just do... I guess we should actually do these same tests that we did for the TD. But we'll just replace all of these with TD link. We'll say TD link is now Q head link. And for each of these guys, we're going to replace transfer descriptor with a Q head. And the Q head has 2 bytes. So this guy says TD is now QH. And is that otherwise good? This is head link, and this should be set head link. Let's just comment these guys out for a second while we test if this compiles. Let's see it. He doesn't like that because I didn't do something. Oh. This function down here, I didn't want him. I did not want him. Are we there? All right. That looks like it passes. And so now we just give the same treatment to the other guys. So this guy wants to test the Q head link to either none or the other to a Q head. So I just kind of whomp this in here and change this val to say QH instead of TD. And this says Q head, so a Q can point to a Q. We test that this is all good. And this now probably has to say 2 like it said before in the other version. And now we do the same thing here, but with none. So this should say Q link pointer none. And here, this should say 0x1 U32. And I think that was it. Cargo test. Let's see it. Come on, baby. Test pass, wonderful. And then we just give the same treatment to the element pointer. So we go here and we say head, and we just replace this with element. And all of these zeros, we are now testing the first element, not the first word, not the 0th word. And I think all of those should pass now too. I think that's easy peasy. Wonderful. All of these are passing. Okay. So that went shockingly easily. Yeah. Yeah, wow, that was easy. Okay, so now the last piece is the frame list. So we program in this guy to the UHCI controller. And these guys just have the same format again, I think, where, let's see. I thought they have the same format where it's like pointer and then these 2 flags at the bottom, but it does look like maybe that there's only 2 flags here. Where do they describe the frame pointer? Frameless pointer. Oh yeah, it's the same shit. Same shit, right? QList, terminate, and the object. So this is just going to look, again, very similar to the Q head. So I guess we make our frame list. Oh, I think we actually have to write repr transparent in all of these as well to make sure that there isn't like extra padding and shit. Nope, it doesn't like that. That's fine. So I think we just say struct frame list, and here we have to be a little careful because why? Because if I've had this problem before where if I were to say frame list is like a 1024 U32s, this is actually just like a massive pain in the ass to construct in Rust. Because if I wanted to like put this on the heap, you can't actually do that without unsafe. So probably what's easier to do here is just force it to be on the heap all the time. And do this. And I think that doing a box U32 is easiest here. So we'll say use alloc boxed box, which is just like Rust's like scoped pointer type. And I wonder if I actually do want a like special type for this. Like I could just put this in a vector. That's probably fine. I'll probably do that. That seems easier for now. So here, I guess in our UHCI device struct, we'll just put like a frame list here. And he'll be like a vector of U32s. And then we'll just say that our frame list is equal to vec 0, 1024. So here, that means that we need first we need to pull in some of the vector stuff from the alloc crate. So we'll say use alloc vec, and we'll use, I think it's like this. But then where do I get the macro from? I thought it was like this. Maybe it's, I do this and this. Which is very confusing. That's a confusing import. Where I import both the macro and the module. Like the macro having the same name as the module is just very confusing, but we'll live. We'll live. And then we'll say for elem in frame list, we will just set link pointer. I guess we'll just do this manually. We'll just say that we want the number 1 over and over again. So we'll say, by default, set the terminate bit on each frame. We will adjust them later. Maybe. Okay. So now what we should be able to do is we should be able to start like working on cleaning up, like resetting the device and programming the frame pointer to each of them. So like what we should be able to do is like put this list in, and then we should be able to start actually like issuing commands. But I actually got farther faster than I meant to today. Oh, I shouldn't say meant to. This went smoother than I expected. And so because of that, I'm not really prepared for the next segment, which would be using these lists, setting them up in a way that lets us actually start asking a device for some info. So I think I'm going to put a pause on it there and come back tomorrow. Actually tomorrow, instead of skipping a day like last time. And from there, it should be pretty easy, now that we've got all of the pieces in place, to start like actually talking to a device. So that's what I'm going to try to do tomorrow. So thanks for watching. If you liked what you saw, I stream most days at around 1 or 2 o'clock Pacific time for around 1 or 2 hours. If you want to come in and say hi and you're watching on YouTube, there's a link to the Twitch in the YouTube description. And if you're watching on Twitch and you're like, fuck, I missed it, because like obviously that's what you're thinking. Yeah, if you missed something, you can always click on the YouTube link in the Twitch description, and that'll take you to where I upload all the VODs. If you want to see the code, there's code on GitHub, which just is under the same username as both my Twitch and YouTube. Yeah, thanks for watching. Catch you on the next one. Bye.